Swayam Prabha. Digital India. Educated India.
In this lecture, we will continue our discussion on coarse-grained MD simulations. So, in the last class, we talked about Langevin dynamics and Brownian dynamics. So, in the Langevin dynamics, we changed the equation of motion to include two additional forces, one that is frictional forces and the other one that is a random force. And the reason for including this is to account for the effect of solvent in the background and focus the attention only on the system of interest, which could be a macromolecule or colloidal particles or nanoparticles. So, we don't want to explicitly treat the solvent, we will just keep that solvent in the background. The effect of the solvent comes via these two set of forces. And then we also discussed a few algorithms by which we can integrate these equations of motion and track the system. Further simplification is possible if you think about some long time dynamics where the momentum variables can be dropped and we can solve only the positional Langevin equation, also known as Brownian dynamic simulations. And we have to remember that this particular random term is basically the random velocity process. This is random velocity process. Whereas in the Langevin dynamics, this is known as random force. And we also looked at the statistical properties of these random forces and random velocity processes in the last class. And one of the characteristic of this particular algorithm is that it does not conserve momentum, and further we do not have hydrodynamic effects inbuilt in this particular algorithm. What we mean by hydrodynamic interaction is that as the particles moves, there could be fluid mediated interactions which can give rise to changes in the dynamics, and that is not encoded in this particular algorithm. But then if you look at the further development on Brownian dynamics, there have been some efforts to include hydrodynamic interactions as an additional set of forces as well, but that is something that we have not discussed. So, now we want to go to another level in terms of coarse graining. We are basically seeking a method which will have hydrodynamics inbuilt, and which is something we can use to simulate fluids, fluid mixtures and self-assembling systems. In principle, many of the software systems involves multi-components, large time scale, length scale separations. So, we are seeking a another coarse grained simulation for such case, and so our objective is to go to larger system size and larger time scale. So, in the context of coarse graining, we can look at this figure. So, on the x axis we have the system size and the y axis we have a computational efficiency. So, here at the bottommost corner, here we have this quantum region where we treat all the electronic degrees of freedom. We think about how charges are distributed, how reactions take place, etc. This is something we have not discussed as part of this course. We started only in the atomistic scale. We did look at molecules and atoms in a classical framework, and then we saw how MD can be done. And from here we can build a coarse grained MD simulation where the system itself, the molecule themselves can be coarse grained, or the solvent can be coarse grained via Brownian dynamics and Langevin dynamics. And there are other scale which are known as this mesoscale, where there is a length scale in the system that could come out because of phase separation, or it can come because of self assembly, which are quite large, which comes between the microscopic and the macroscopic world, and this is called mesoscopic regime. And then if you go all the way up, you go basically to the continuum mechanics regime, where you look at the problems in terms of Navier-Stokes equations and conservation laws. So, now we are basically going to talk about a technique that basically falls in this mesoscale, and in this particular mesoscale, the structures that are formed are quite large, that cannot be handled by simple MD simulations. At the same time, we cannot treat them in terms of continuum mechanics either. So, we want something in between, a mesoscale simulations. And we also see in this particular length scale, the hydrodynamic effect also becomes very important. I will show you one example with and without hydrodynamics, how the self-assembled structures could be very different. So, we are looking for a new coarse-grained simulation, dynamical simulations, which will incorporate fluid mixtures in a mesoscopic length scale and time scale. So, the approach is given by this dissipative particle dynamics. In short, it is known as DPD. So, in this particular method, we think about a DPD bead, or we call it as a DPD bead, that typically represents not just one or two atoms of molecules. It has a group of particles of the fluid considered as a DPD particle. So, as you would imagine, then this DPD sphere is supposed to be very soft, because it encodes a large number of atoms and molecules effectively treated as one DPD particle. So, in this between these DPD particles, we include a dissipative force, and that depends on velocity difference between the particles. And then we also include a stochastic force directed along the line joining the two particles from center to center. So, just like how we did in Langevin dynamics and Brownian dynamics, in this DPD simulations also we include a dissipative force and a random or stochastic force. And this is pictorially shown in this particular figure, where you have two particles centered here, and these two particles interacts via a conservative force, which would be related to inter and intramolecular forces. And then there is this dissipative force, which is nothing but a damp, which is known as a dashpot here. And then there is a stochastic thermal noise shown as a random noise here. So, the point of doing all this is basically, we want to basically build a DPD bead that will represent as a minimal model for representing the viscous forces and thermal noises between group of atoms, which we have considered as a one DPD bead. And so, when you look at this combination of this dissipative and stochastic force, this is known as a pairwise Brownian dashpot. And in this particular DPD simulations, the forces are chosen such a way that the momentum is a conserving quantity, and that is the basis why the hydrodynamic interactions are taken into account automatically in the system. And this is something that was missing in the Brownian dynamics, where the momentum was not conserving. So, now let us look at the details of equations and discretization of this particular method. So, we have basically the rate of change of the momentum is equal to force, but this force Fi comes from pairwise addition of conservative forces, dissipative force and a random force. And then when we solve this particular equations, we basically get a distribution given by a canonical distribution. So, this basically a NVT simulation. Okay, we are not going to show the proof of this result, but we will consider this as a fact that DPD simulation is essentially an NVT simulation, sampling the trajectories via a canonical distribution. So, now if you look at the conservative force, again we are not thinking about DPD bead as individual molecules, but we are thinking about large collection of molecules treated as one soft sphere. Okay, and then if you look at the interaction between those spheres, it is considered to be a very simple soft repulsive force given by a simple linear law. So, here this force is given only up to certain cutoff distance RC. Beyond this RC, it is basically 0. So, you can also see that this force, so when Rij, which is the distance between the two particles, is equal to 0, that means we have a overlapping two particles. In that case, this force becomes maximum, that is Fij will be equal to Aij. So, this Aij here is basically a repulsive parameter that says how much repulsion you want to add whenever the two particles overlap. So, we are talking about a soft sphere model. This is very different from hard sphere model, because in hard sphere model the moment they touch, the potential goes to infinity, whereas in the soft sphere model we allow finite overlaps. In fact, when Rij is equal to 0, we are basically talking about two particles sitting on top of each other. Even in this case, the repulsion is given by Aij, which is a parameter that as a user one has to define it. but this force will decay from Aij to smaller and smaller value as this overlap becomes lesser and lesser. And this interaction basically goes to 0 the moment the two particles are at a distance of RC and beyond. So, this is the nature of conservative force that has been proposed in this particular DPD simulation. The fact that it is a very simple linear force allows you to take a very large time step, and this something has to be contrasted with other forces, something like Lennard-Jones or other short range forces, where the curvature of the potential limits how much delta T you can use. The steeper the potential, smaller the delta T you have to use. Smaller the delta T, only you can reach a short time scale simulations. Whereas the fact that the DPD allows you to take a very shallow potential, shallow repulsive potential, allows you to take a larger delta T, so you can actually simulate a system for a very long time scale simulations. So, that is one of the feature of this conservative force. Apart from this, if you want to add any additional forces, that is also possible. We are talking about the basic version of DPD. A lot of modifications have happened where we can include additional conservative forces as well. And then there is this dissipative or drag force, so which is defined by a lot of terms here. So, we have this the noise term gamma, it basically says the strength of the dissipative force, and then there is some weighting function W or omega d here, and then this force is basically proportional to the dot product of Rij dot Vij. So, the moment that the radial relative velocity between two particles, when they become different, then this dissipative force acts on and then tries to bring down the difference in the radial velocity of two particles I and j. And this force act along the contact line between I and j. Rij vector, Rij unit vector here is basically the direction of the Rij vector. Similarly, if you look at the random force, this also has a amplitude of the noise, and then there is a weighting function omega r, and then there is this random number theta ij, whose statistical property basically is given by this, basically a Gaussian noise, and then it also acts along the interparticle distance vector. So, now the form of this dissipative and random force is quite different from what we have seen in Langevin dynamics or Brownian dynamics. The fact that they are chosen such a way is that to make sure that the momentums are conserved and the hydrodynamic interactions can be taken into account. So, I have highlighted some parameters in blue basically because these are the ones that as a user will have to define what is the repulsion parameter, what is this random force amplitude sigma and dissipative force parameter gamma, etc. So, it turns out that these weighting functions that we talked about in the slide, the weighting function omega d and omega r, these are not really independent, they are actually related to each other. That means choosing one will automatically fix the other because of the underlying momentum conserving constraint. And similarly, the noise between the thermal and the dissipative components also is related. So, all we have to do is choose either omega d or omega r, the other one is automatically chosen. Similarly, choose either sigma or gamma, one of them is enough, the other one is automatically fixed. So, in most of the situations, we define this omega d, which is a weighting function, as a simple quadratic equation as 1 minus Rij whole square up to some distance cut off Rc, and beyond it is 0. So, you can see that omega d is equal to omega r squared. So, both functions are defined by this particular expression. So, then one can use a certain type of discretization algorithm to solve the dynamical equations given in this set of equations. So, if you look at this particular algorithm, we first update the particle positions, DPD particle positions using the current position, current velocity and the current force. And we have to remember this force is a sum of all the three forces: conservative, dissipative and random force, all put together. So, with this then we also calculate the velocity Vi bar using the current velocity and the current force, and then a small parameter here lambda is also added here, and the value of this lambda is also something one will have to fix. And once we do this, then we calculate the new force at t plus delta t using the new position and the new velocity we just calculated. So, this V I bar comes from here, and similarly this R comes here. So, once we have updated the new positions and new velocities, we calculate new force, and then the second step we update the velocity one more time using the forces of the current step as well as the force of the next time step, which we just calculated here. So, you can imagine this is basically analogous to the velocity valley algorithm we used in MD simulations in 2 steps, where we use forces calculated at the current time and then the next time together, and then we calculate the velocities. So, now if you look at this algorithm and if you see this, if the force are independent of velocity, and then we will see that, so what this basically means is that FD should go to 0, because that is the one that depends on the relative velocities. And then if you choose lambda equal to 1 by 2, you can show that this whole algorithm basically converges to a simple velocity valley algorithm that we have seen before. So, in other words, we have basically taken the basic velocity valley algorithm and then we have applied this for DPD simulations using certain parameter lambda. When lambda is equal to 1.1 by 2, then we basically converges back to velocity valley algorithm. So, now we may wonder why we have this particular constraints on the parameters of random force and dissipative force. The reason is the following, that if you look at canonical MD simulations, we know that the distribution function of the phase space is proportional to exponential of total energy divided by kBt. And so, now when we include the dissipative and the random force, we do not want to disturb this particular distribution. So, in order to maintain that condition, we basically have to derive a set of relations by looking at how these random force and dissipative forces are applied. They have to satisfy a certain condition such a way that the distribution is not changed. So, that is the reason why we find a relationship between the parameters of dissipative force and random force given by these 2 equations. So, essentially we have to remember that DPD is nothing but an NVT simulation, okay, and which preserve the hydrodynamic interaction between the particles. And like I was saying, the conservative force that we have taken is very shallow, linear in R, and that basically allows you to take much larger time step that is than that is commonly used in MD simulations. This is the reason why we say this is a DPD is a mesoscale simulation, because it can reach longer time steps and longer simulations while preserving the hydrodynamic interactions. So, in DPD simulations, we also use set of basis units, and you have to remember that in DPD bead there is no size mentioned. Okay, this is because we are talking about a DPD bead as a collection of atoms. And so, typically what is done is, since there is no length scale in the system as such, because there is no molecular diameter in the system, so we consider the cutoff distance of a web that we chose as the length scale. So, the length scale RC is taken to be 1 as a basis unit for the length, and mass is kept as 1, and then energy is given in terms of kBt is equal to 1. So, once you choose mass, length and energy parameter, time is automatically fixed, which is given by RC times square root of m by kBt, and that also will become 1. And the reason why we have written this particular value is that if you look at an Lennard-Jones unit, we would have defined this in terms of molecular parameters, something like this, where sigma is the Lj size, mass, and epsilon is the Lj well depth. So, we are writing something analogous to this expression, where instead of sigma, we choose the length scale as to be the cutoff distance. And since there is no energy scale as well, so we take kBt thermal energy as the energy scale. Okay. So, this is something we have to keep in mind when we do DPD simulations. So, now when you want to use a DPD as a mesoscale simulation method, as a user, you have to make a decision about what are the set of parameters that are needed. So, for example, for the integrator perspective, we want to choose what is the delta t and what is this parameter lambda. So, you have to recall this lambda is nothing but that comes in the velocity update in the integrator step. Okay. So, this lambda is something that one has to specify along with the delta t. Then we also have to specify the noise amplitude sigma, and then this dissipative force amplitude gamma can be obtained from this relationship that we saw. In addition, we also need to find out what is the repulsive parameter, because this is something that tells you what is the repulsion between two DPD beads. So, these are set of parameters that we will have to choose before doing the simulation. So, now we are going to discuss few points how to go about choosing these set of parameters. So, now the first thing is to choose delta t and the noise amplitude. So, in this case what is being done is a set of simulations are typically done where you change the delta t in the simulation and then for different lambda values. For example, you can forget about these curves if you focus only the bottommost two curves. So, we are looking at an algorithm, velocity Verlet algorithm, where the lambda parameter is either fixed at 0.65 or at 0.5, and then we are looking at the simulation at a different time step and calculate the change in the temperature. So, kBt is taken to be 1. So, when you say kBt minus 1, ideally you want this to be 0, but it is not essentially 0 because we are looking at finite time step simulations, but the smallest value is what we prefer. So, if you look at the bottommost curve 0.65 and the time scale goes from 0.01 to let us say 0.1. In this range you can see that the error in the temperature is not exactly 0, but it is close to 0, it is 0.001 or even below, and you can see that as up to this particular time this remains pretty low, and then if you starts increasing the delta t in the simulation, you can see it shoots up, the temperature goes beyond what is being set, and same thing is found for lambda is equal to 0.5, it is slightly above than lambda is equal to 0.65, but it also shows a very similar characteristic that at a very small time step delta t this error is very small, and then for longer higher and higher delta t, then this also grows up. So, one will have to do a simulation of this kind for a given system and find out what is the sensitivity of delta t, and then see what is the acceptable error in the temperature difference, and then one will go. So, clearly one should not take delta t in this regime, because this is where this temperature starts drifting. So, so typically for a plot like this, one would suggest delta t can be something like 0.04, which is somewhere here, okay, and then lambda can be either 0.65 or 0.5, because the difference is not very much. So, you can take either this or this, okay. So, similarly, so this whole simulation is done for a fixed value of the noise amplitude sigma, and if you fix lambda and then do the simulation for different sigma values, and then you will see a similar trend. That means higher the noise amplitude, larger is the error. So, you have to look at some bound with which this sigma value can be chosen. So, one will have to study a sensitivity analysis for all the parameters. In this case, we have shown for delta t and lambda, but similarly one will have to do for sigma also. So, based on this, one will have to typically choose, if you look at literature with DPD simulations, you will see typically delta t to be 0.04. Again, this is something related to the time basis units I just now discussed. And then this sigma which is a noise amplitude can be of the order of 3, and lambda is typically either 0.5 or 0.65. This is one way to choose time step and noise level. The other important thing is to find out this repulsive parameter A. Okay. So, to see this parameter, let us go back. We define this conservative force in this expression, and I said that the repulsion force would be equal to Aij when two particles sit on top of each other. So, that is basically the maximum repulsion, and this is a parameter that one will have to decide. So, we decide that parameter repulsion parameter by ensuring that the simulation correctly predicts the compressibility factor of the fluid in case. So, so what we do for that is, first of all, we define dimensionless isothermal compressibility. So, to recall, compressibility is something like when you change the pressure, how the when you change the volume, how the pressure changes. So, that is given by isothermal compressibility, but here we are writing in terms of some non-dimensional quantity. kappa inverse here is basically the non-dimensional inverse isothermal compressibility, and so this is not n, this should be rho. Rho is the density, kBt is the Boltzmann constant times temperature, and this is the so from the 1 by kBt dou p by dou rho, something like this. So now what we can do is we can actually do a DPD simulation with the different values of A. Okay, so you choose different values of A, and then if you plot how the pressure changes with density, that's basically the equation of state. You draw equation of state and then get the equation of state, plot it as P minus rho kBt by A. So here what we are trying to do is we are looking at only the excess pressure, because rho kBt is the ideal fluid pressure. So P minus rho kBt will be the excess pressure, and that is divided by this parameter A. So you are doing several simulation with the different sets of A value, and then now you are normalizing all these simulation values with respect to A, and then when you plot this P minus rho kBt by A versus rho, you see this nice quadratic expression for the pressure, and this is basically nicely fitted with a constant alpha, which is typically about 0.1. So now we take this expression and then substitute this pressure in this expression, and then calculate what is the non-dimensional isothermal compressibility. So in this case, you can see if I substitute P here, the first term becomes just kBt, the second term will become 2 times alpha A rho, and then you have to divide by kBt, then the first term will be just 1 and the second term becomes 2 alpha A rho by kBt, and then if you substitute for alpha here, which is 0.1, you will see that the non-dimensional isothermal compressibility becomes 1 plus 0.2 A rho divided by kBt. Now if you look at these values for simple fluids like water, it seems that the non-dimensional isothermal compressibility comes out about 16, and then now you match these two expressions. This is experimental value and this is the predicted value. You match that and then find out what is the value of A should be, so that the DPD simulation correctly predicts the isothermal compressibility. So if you want to simulate water in a DPD simulation, and if you are hoping to predict isothermal compressibility equivalent to an experimental value, you should be choosing the repulsive parameter A by this particular value. A should be 75 times kBt by rho. So for any other fluid, this is a way to go forward. You look at isothermal compressibility, measure it in DPD simulation for different repulsive parameters, and then you match that with experimental value, and then choose the correct value of repulsion parameter. Now one of the problem with this particular approach is that you see that the value of A depends on the density of the system. That means anytime I change the density of the system, I will have to tune this parameter again in this case. So you have to change the parameter A. This is typically not the case if you think about our typical MD simulations, where we do not change the parameters of the potential when the temperature is changed, or when the pressure is changed, or when the density is changed. But here, because of the way we are doing this coarse graining, and we are actually forcing the comparison between isothermal compressibility to be equal to the experimental value, we end up in this situation where the potential parameter, in this case A, again becomes depends on the density of the system itself. So every time you change the density, A has to. There's another problem with the DPD simulation, that is to do with the dynamics. So as far as the equilibrium thermodynamic properties are concerned, you can sample properly, you can get equilibrium properties calculated accurately, etc., including hydrodynamics, interactions, and momentum conservation. But when you look at dynamics, so what we are talking about dynamics is that at what rate momentums are diffusing, at what rate mass is diffusing, etc. So to see the problem with the dynamics of DPD, so we first look at this the definition of Skibin number. This is something we often use in chemical engineering when you look at simultaneous mass transport and momentum transport together. So the Skibin number is basically a ratio of momentum diffusivity by the mass diffusivity. In other words, it's a ratio between the kinematic viscosity to the mass diffusivity. And then for water at room temperature, if you look at the values of kinematic viscosity and diffusivity, you will see the Schmidt number is of the order of about 1000. and for other liquids like alcohol and other, you will see something similar numbers. This basically means that for a system like water, the momentum diffuses 1000 times faster than the mass. So that's the meaning of Schmidt number being 1000. So now we want to see for the typical parameter set that we use in DPD simulation, what does the Schmidt number look like? How is this momentum transport and mass transports are coupled, and what is the rates, relative rates of those? So to see this, we have to look at the expression for the viscosity for DPD particles. Again, we are skipping the derivation where this is coming from. So we take this expression here. This eta d is basically the contribution of the diffusive force or dissipative force on the viscosity, and we also have the momentum part, etc. So if you look at this expression, we basically have a integral over r with the weighting function omega, and omega is something that we have already chosen. So analytically you can calculate this, and that is shown here. So once you calculate eta d, and then you can calculate what is the dissipative contribution to the kinematic viscosity nu, which is nothing but eta by rho, and then this comes out to be certain expression, and this depends on what is the dissipative amplitude gamma, what is the density, and what is the parameter RC that is being used. Similarly, we also can calculate what is the diffusivity in DPD simulations, and we can use Green-Gubbo relations, and then in this thing the parameter tau is again related to the omega d, the weightage function. So again we can analytically calculate the expression for d also, and then if you look at the total viscosity for DPD simulations as well as total diffusivity for DPD simulations, you can derive an expression that is a function of the parameters that we choose. In principle, the gamma, RC, and the system parameter like density. So now we have this expression for total kinematic viscosity and the total diffusivity. The reason why I am calling total is because we are adding up the effect of dissipative and thermal contributions in the kinematic viscosity, and similarly on the diffusivity also. So we take these two expressions and substitute here, and then you see that the Schmidt number becomes some expression 1 by 2 plus set of parameters, and then we already discussed what are the typical values of gamma, RC, etc. and rho. If you put the numbers, it turns out that for DPD simulations, the Schmidt number is of the order of 1. The meaning of this is that the mass is diffusing as fast as the momentum, but in real situation that is not the case. So we have a kind of an artifact in the dynamics of mass by amplifying its dynamics. So if you have any simulation where the mass diffusion is rate controlling or having an important role, then the DPD will have a very strong bias because of the incorrect dynamics. Ideally, one would like to have a Schmidt number equivalent to something like 1000 or of that order, but it turns out that while we enforce momentum conservation, hydrodynamic interaction, etc., dynamically we have kind of we see a situation where the mass diffusion is quite fast compared to comparable to momentum diffusion. So the one way you can mitigate this problem is that you can see this in this particular expression. You see the Schmidt number is proportional to gamma square, and gamma is a parameter that we choose via choosing this sigma, and for this we have looked at sensitivity analysis before. So one way to do would be to look at a slightly larger and larger value of gamma, and then this Schmidt number can be increased a little bit. So there is a hope to improve by systematically changing the parameters so as to match the experimental Schmidt number and the DPD Schmidt number, so that the dynamics is also captured. But in general, one would not use DPD simulation for dynamical properties. It is usually used for predicting phase behavior or calculating equilibrium dynamics. So here is an example that a same system is simulated using two different types of simulations. One is Brownian dynamics, and so this box is basically the boundary here. That is kind of a copolymer, I would say. Two dissimilar polymer components are covalently bonded together. It's called copolymer, and the copolymer is actually simulated by either Brownian dynamics or a DPD simulation. it is found that in the DPD simulation, the system formed a hexagonal phase that you can see as a layer as going across this. Whereas in the Brownian dynamic simulation, the system remains trapped in a metastable state, which shows an interconnected network of tubes. So, the fact that in DPD we have hydrodynamic interactions, it appears that the DPD simulation allows the system to be sampled such a way that any of this metastable state can be easily overcome by crossing the energy barriers. So, the hydrodynamic effects are very important in dictating what is the phase behavior is. If you incorrectly looked at only this simulation, BD simulation, you would have predicted this phase behavior where this is stuck at some metastable state. But if you had included the hydrodynamic interactions, that could have given a more experimentally realistic ordered phases, and that is mainly coming because of the fact that we have hydrodynamic interactions in the DPD. And this is also shown as a function of time, that if you define some order parameter that can distinguish between the hexagonal phase and the other phase, the DPD simulation order parameter increases as a function of time, whereas the Brownian dynamics kind of getting stuck at somewhere here. Okay, and Brownian dynamics is not able to overcome the energy barrier to sample the more ordered states like hexagonal phase here. This basically tells us that when we look at coarse grained simulations, sometimes we have to look at the effect of various things. So, we cannot just do only Brownian dynamics hoping that hydrodynamics is not important. We will have to augment such simulations with incorporating hydrodynamics and ensure hydrodynamics whether play a role or not. Okay. So, in this particular example, clearly hydrodynamics seems to be playing a role. And another example would be looking at some phase behavior of surfactants. So, you can see this is a surfactant, long chain surfactant. There is a head group here and there is a long tail, and this is modeled as a two sphere coarse grained. So, in this simulation, the surfactant is coarse grained by a DPD bead with the two beads connected by a bond, the C bead and D bead. So, C bead represent the alkyl chain and the N bead represent the head group, and water is again modeled as a DPD sphere. So, with this they were able to predict various mesoscopic phases that are found in this surfactant, and the phase diagram is also constructed. And if you are willing to do something like this in a pure MD simulation, this won't be really possible, because you can see the mesoscopic structure that are formed are quite high. That means in MD simulation you should have used very large number of system to see this kind of phases. So, that is where this coarse graining becomes important, where we might have compromised on the dynamics, but as far as the equilibrium structure is concerned, we are able to get close to experimental phase behavior. Okay, so with that, so we can summarize this DPD is a dissipative particle dynamic simulation, is a mesoscopic simulation which is useful for simulating fluids and fluid mixtures and surfactant systems and polymers. And in this case also we have, like Brownian dynamics and Langevin dynamics, we have a random force and frictional force, because of which this energy is not conserved and it becomes an NVT simulation. We can use a standard discretization method like velocity Valley algorithm with random numbers and some parameter lambda, and the random force and friction force or the dissipative force are chosen such a way that the momentums are conserved, and by which the hydrodynamic interactions are also included. And we have to recognize that DPD also has certain limitations, and these limitations are very high mass diffusivity and leading to some incorrect dynamics. And there are other issues, something like because it's a constant temperature simulation, it's a dissipating energy and then maintaining the temperature constant. So, if you want to do a non-equilibrium simulation with an imposed temperature gradient, that will not work. And similarly, we also saw that the potential parameter that we choose by mapping the experimental isothermal compressibility led to density dependent potential parameter. So, that means every time we change the system's density, we have to refix our potential parameter, which is something